Okay, hello everybody. So if you remember the last time we were talking about the centrifugal compressors, and we gave some examples to you. Now we are going to have a look at the turbines, especially the axial flow turbines. So first of all, we are beginning with some introduction on the hydraulic turbines, and the reason that so many different types of um turbines are in use is because of the almost infinite range of service requirements. And generally, for a given set of operating requirements, one type of turbine is best suited to provide optimum conditions of operation. In hydraulic turbine, water is used as the source of energy, and water or hydraulic turbines convert this kinetic and potential energies of the water into mechanical power. The main types of turbines are impulse and reaction turbines. The predominant type of impulse machine is the Pelton wheel that is shown in here to you, which is suitable for a range of uh, between 100 to 2000 meter head. The reaction turbine is further subdivided into the Francis type and is characterized by a radial flow impeller, and the Kaplan or propeller type, which is an axial flow machine. As we said, all turbo machines can be classified as either impulse or reaction machines according to whether the pressure changes are absent or present, respectively, in the flow through the rotor. So, if the rotor can change the pressure, we say that it is a reaction turbine. If it cannot, it is an impulse turbine. And in an impulse machine, actually, all the pressure change takes place in one or more stators or nozzles, we call them, and the fluid being directed onto the rotor. And as we said, the Pelton wheel, we are not calling it exactly as Pelton turbine, but sometimes we say the Pelton wheel is an example of an impulse turbine. So I'm gonna show a video, a short movie on these three different types of hydraulic turbines right now to you, and then we will continue. Okay, in here, as we said, the axial flow gas turbine is used in almost all applications of uh, gas turbine power plants. And the development of the axial flow gas turbine was actually hindered by the need to obtain both high enough flow rate and compression ratio from a compressor to maintain the air requirement for the combustion process and also subsequent expansion of the exhaust gases. The axial flow type has been used exclusively in aircraft gas turbine engines to these days, and it will be discussed in detail in this lecture. The axial flow turbines are also normally employed in industrial and shipboard applications as well. This figure that you show in the right uh, shows the rotating assembly of the Rolls-Royce engine, and it's showing a typical single-stage turbine installation. On this particular engine, the single-stage turbine is directly connected to the main and cooling compressor. So, and the axial flow turbine consists of one or more stages, just like the compressors, located immediately to the rear of the engine combustion chamber. The turbine extracts kinetic energy from the expanding gases as the gases come from the combustion chamber and converts this kinetic energy into the shaft power to drive the compressor and the engine accessories. And as I said, this figure shows the axial flow turbine, only the rotor blades. So the stator or nozzle guide vanes are not there. In the case of reaction turbine, we said that the pressure drop of expansion takes place in the stator as well as in the rotor blades. So the blade passage area uh, has to vary continuously to allow for the continued expansion of the gas stream. And the efficiency of a good design turbine is higher than the efficiency of a compressor. And the design process is often much simpler because we said that the turbine is working in favorable pressure gradient, but the compressor is working in adverse pressure gradient. And and in the compressor, fluid undergoes a pressure rise, and it's much more difficult to arrange for an efficient deceleration of flow than it is to obtain an efficient acceleration. The pressure drop in the turbine is sufficient to keep the boundary layer fluid well behaved and separation problems or breakaway of the molecules from the surface, which often can be serious in compressors, as we saw, and it can be easily avoided in turbines. However, the turbine designer is facing much more critical stress problems because the turbine rotors must operate in very, very high temperature of the gases. So, um, uh, in here, in this slide, let me check that. Yes, I am recording. I was thinking that I'm not recording. Okay. In this slide, uh, there is a schematics in here to show you the comparison between a pure impulse turbine and an impulse reaction or a mixed turbine. So we said that there are three types of turbine. As in hydraulic turbines, we have impulse, reaction, and a combination of the two that is known as impulse reaction. In the impulse type, the total pressure drop across each stage occurs in the fixed nozzle guide vanes. And because of their convergent shape, uh, increase the gas velocity and decrease the pressure happens. The gas is directed onto the turbine blades, which experience an impulse force caused by the impact of the gas on the blades. In the reaction type, the fixed nozzle guide vanes are designed to alter the gas flow direction without changing the pressure. And the converging blade passages experience a reaction force resulting from the expansion and acceleration of the gas. Normally, gas turbine engines do not use pure impulse or pure reaction turbine blades, but they use a mixed combination. So this mixed is, as you can see, is shown in the right side, and the proportion of each principle incorporated in the design of a turbine is largely um, dependent on the type of the engine in which the turbine is operating. But in general, it's about 50% impulse and 50% reaction. Okay, let's have a look at the Euler equation, and let's have a recap of the Euler equation here. So you remember that the power of shaft was equal to mass flow rate times velocity times the difference in tangential velocity. So why we call it V theta 3 and V theta 2, you can refer to your old notes. It's the difference between tangential velocity that is happening in the rotor. And we said that this is equal to the change of the total enthalpy between station 2 and 3. And so for turbines, you will end up with a positive shaft power that is showing you that you have some power as output. So if you look at the configuration, you will see some nozzle guide vanes and then the rotor blades. So in the nozzle guide vanes from 1 to 2, from station 1 to station 2, you see that the stator does not change the stagnation properties, so your stagnation enthalpy remains constant. That's why we are writing the power of shaft is equal to the difference of the total enthalpy from 2 to 3. And you see that just by expanding the air or the gas, the rotor blades are dropping the total enthalpy, so your enthalpy at point 3 is less than your enthalpy at point 2. There are some notes like we said there can never be a rotating installer surge in turbines, and we said that the static pressure drops through the expansion and the stagnation pressure drops within the rotor. So usually you have to check the choked flow and the limit for the mass flow rate as well. And usually the absolute velocity at rotor inlet is supersonic. But because of rotation, your peripheral velocity u, you have your relative velocity that is subsonic. So we say that the relative Mach number is less than 1. So there is a throat in between two blades passage. So if you just look at the blade to blade view like this, what is showing like this, you can see that there is a throat there, and this throat over there it has the minimum area location, and it's possible to have your relative Mach number equal to 1 at this throat area. So when it is reaching the Mach equal to 1, you all know that the flow is choked there. So you have uh, face a maximum mass flow rate there. So this is the limit on the mass flow rate there in the blade to blade passage. Now we want to just compare the compressor and the turbine and see what is the difference between these two in this slide. So the first thing is that your total pressure, total temperature, and total enthalpy all are drop down through a turbine rotor. The compressors operate at much lower temperatures than turbines. And as we have today, we have some turbines that the TIT or turbine inlet temperature can reach up to 2000 Kelvin. We have a much higher flow turning angle in turbines. So compared with compressors that have 20 to 35 degrees of turning angle, the turbines can go up to 140 degrees. We also have considerable difference in blade thickness, camber, and the profile shape in between turbines and compressors. The annulus area increases in turbine, while in the compressors it is decreasing. The material considerations are much more critical for turbines because we said we have a very high rotating RPM with very high temperature there in turbine. And also we have the favorable pressure difference and fewer stages in turbines as well. Okay. Uh, so as we said, we have this problem of very high temperature in the turbine. So this is an important consideration at the design stage of a gas turbine engine, and it is the need to ensure that certain parts of the engine and in some instances certain accessories do not absorb heat to the extent that is detrimental to their safe operation. The principal areas which are require air cooling are the combustor and turbine. So right now we are dealing with the turbine blades. This high thermal efficiency is dependent upon high turbine entry temperature, which is limited by the turbine blade and nozzle guide vane materials. Continuous cooling of these components allows their environmental operating temperature to exceed the material's melting point without affecting the blade and vane integrity. The heat conduction from the turbine blades to the turbine disc requires the disc to be cooled and thus prevent thermal fatigue and uncontrolled expansion and contraction rates. There are some ways to do this, let's say, uh, containment from the high temperature. And the first thing is the single crystal casting or SCC. So single crystal cast plates are grown from a single crystal in a vacuum casting furnace from some super alloys, and they increase the turbine's efficiency and individual blades service life, and they give it very high resistance to high temperature creep and fatigue. And at the picture at the left is showing to you the comparison between methods of casting. So we had some conventional casting methods with ceramic mold, and then we had some directional solidification and the single crystal blade, which is shown at the uh, right. It's something that is uh, very beneficial for the turbine blades right now. So in the right picture in here, you can see the schematics showing how they make single crystal turbine blades in a mold inside the vacuum furnace. So this is a furnace and there is a vacuum. You have the radiation heating and it is molten metal, and they are putting it inside and they make it as a single crystal. Another way is called TBC or thermal barrier coating, and these thermal barrier coatings are some advanced materials systems usually applied to metallic surfaces operating at elevated temperatures. Uh, and these coatings are varying in the size from 100 microns to 2 millimeter thick. And these materials serve to insulate the components from large and prolonged heat loads and can sustain an appreciable temperature difference between the load-bearing alloys and the coating surface. So, as you can see, you have your substrate in here, and then you have one layer of metallic bound coat, and then the thermally grown oxide and the thermal barrier coating at the outer layer. And then the hot gas is passing from above the TBC, and you also can do some cooling from the inside that we are going to see it in a second. So the third way, or the third let's say thing that we use in order to contain the high temperature is the cooling of the blades, as you can see um, in this slide. So you have an air-cooled high-pressure nozzle guide vane and turbine blade arrangement at the left side, at the left figure. The turbine vane and turbine blade life depends not only on their form that we were discussing from a single crystal casting and these things, but also on the method of the cooling. Therefore, the flow design of the internal passage is very important. And there have been numerous methods of turbine vane and turbine blade cooling which have been used throughout the history of the gas turbine. And generally, single pass internal cooling was of a great practical benefit, but development has led to multi-pass internal cooling of blades, which impingement cooling of vanes with external air film cooling of both vanes and blades were used, and these are shown in these three figures at the right. And if you notice, there is a pressure nozzle in the left figure at the bottom of the left figure. This reduces the temperature and pressure of the cooling air fed to the disk for blade cooling, and the nozzles also import a substantial wear velocity to assist efficient entry of the air into the rotating cooling passage. So the next slide uh, has let's say a video about the fabrication of a turbine blade. So let's watch it together and then we will proceed.